Good afternoon and welcome to today's webinar, Machine Guarding, Tamper Resistance and Fault Masking, presented by EHS Today, New Equipment Digest, and Machine Design. My name is Travis Hessman. I'm the Editor-in-Chief and Content Director for New Equipment Digest, and in just a moment I'll be turning things over to our speaker for today. First off, I'd like to thank Schmersal for sponsoring this afternoon's webcast. And before we begin, I just want to explain how we can all participate in today's presentation. First, if you have any technical difficulties during today's session, first step would be to hit the F5 button to refresh your webcast console. If you need any assistance for some common issues, click on the Help button below the slides, and that should help get you through. Now, of course, we welcome your questions during today's event. You just type your question into the question window to the left side of the screen and then hit the Submit button. We will answer as many of these questions as possible during the Q&A session that follows the main presentation, but please feel free to send your questions at any time during the presentation. Please also be aware that today's session is going to be recorded and will be available on New Equipment Digest website within the next week. You will be notified by email when the archive is available. Now, let's introduce today's speaker. Mike DeRocher is a TUV certified functional safety engineer for machinery. His 20 years of experience include controls engineering to design, build, and integrate full machine control systems. The safety experience led him to help corporations develop corporate safety standards, perform machine guarding risk assessments, machine safety training and design, as well as implementation of safety systems for all aspects of machinery, including electrical, electronic, pneumatic, hydraulic, and mechanical. And that's it for that. So let me turn this over to our presenter. Mike, the floor is yours.
All right, thanks, Travis. Good afternoon and good morning, everybody. Appreciate everybody taking the time to attend the webinar today. Past webinars, we may have been a little bit more generalized on a specific topic, but in this case, we thought it might be best to cover something a little bit more detailed as far as specifically what we titled Tamper Resistance and Fault Masking. With changes in the standards that have come about over the last couple of years, more things we've learned, we come across, we see technical reports, and we'll cover a couple of those aspects when it comes to design of machines and why we're looking at things such as tamper resistance and fault masking. So as Travis had said, please, if you have questions, type them into the field. We'll get to as many questions as we possibly can. So as we start, we're going to start talking about tamper resistance. And as much as we've done that in the past, it's even getting more so in looking at tamper resistance of designs. And one of the reasons for that has been based off of studies that have occurred in Europe, one by BG, the other one by SUVA, which is in Switzerland. They've done several studies and things related to machine guarding and accidents and bypassing and defeat, and have done interviews and took both site and field surveys, talked to EHS personnel at different facilities. And the interesting thing that came as a result of that survey, you can see some of the slides percentage graphs there, that the percentage of bypass guards were a total of 37% of either being temporarily or permanently bypassed. And the serious accidents occurring, 25% was due to bypass guards. That's a huge number, and we needed to look at why are guards being bypassed to begin with. So as we start down this path, we want to look at the reasons of why guards are being bypassed. I think we all know that they shouldn't be, but there ends up being, whether you want to call them reasons, legitimate reasons, or excuses of why guards are being defeated. most of the time, and this is not an all-encompassing list, when you look at production requirements, people feel that guarding might be in the way. They need to push production out. They're got problems with speed, that opening and closing guards becomes an issue. Having to clear jams. The machine is jamming a lot more than it used to, so you start seeing guards getting pulled off and defeated to get the jam out and get the machine running again. It makes it easier to use without having guarding, and the convenience factor. When people look at how guards are being used or machines are being used, and if they feel that the guard's in the way, it's more convenient to pull them off or remove them or bypass them, thus making it easier to run the machine and speed things up. The other thing is easier to see the process. When you have solid panel guards over a machine, and whether it's an operator or maintenance trying to troubleshoot or see what's going on, when you can't see through the guard, it makes it difficult to try to troubleshoot. Thus, guards are getting removed under running conditions. Not saying any of these are legitimate, but they're all the reasons you typically find when you start finding issues with guarding or finding bypassing. So we're going to look at a couple of those different issues. And because of that, when you see that, when we have that note danger up there, this is where injuries are occurring because of defeated guards. So with that, what are we seeing? How is it being defeated that are leading to injuries? The list up there, we're going to go through a couple of different examples of each one of those lists. And one of the big debates that we get into is the use of a tool, whether it's considered willful intent because the tool was used, or is it a common tool? You know, whether you have special tools versus common tools, and we'll talk a little bit about that as well. Walking around with spare actuators to stick into the safety switch so somebody can open up the door and run the machine in a full automatic mode. Looking at the design in the switches, or even as far as getting into the control cabinet with electrical bypassing and willful defeat. So the first one we're going to look at is hardware not requiring tools. I think you'd be amazed at how many times you actually see this, whether it was designed that way or over time the machine hardware was changed so it was easier and quicker to get into the guard. You see fasteners like this, either the little thumb screws like you see on the left-hand side of the page, or that little quarter turn knob that's a mechanical latch to hold a door or guard in place. As a result of that, the guards are being removed without any shutdown, even though it might be under a lockout-tagout condition. This is not willful intent. It is designed to be removed by hand without any special tools. If it's a guard that needs to be routinely removed, instead of being a fixed guard, you may want to look at it being a movable guard, and you put an interlock switch on there to ensure that the guard is always put back into place before the machine is allowed to run. So you have to look at the different situations. We did our past webinar back in December looking at lockout tagout versus machine guarding, when you can use one over the other. But this falls into that criteria. Why are you removing that guard? What do you need to get to? Is it a normal, routine, repetitive task? Should it be interlocked? Or does it need to be a permanent fixed guard that's only there for maintenance reasons under a lockout-tagout condition? The next one we're going to look at is common hardware or missing hardware. When you start doing surveys of equipment, as you can see on the bottom left picture, hardware is not being put back in. Usually one of two reasons. Either lost the screw, didn't go get a new one, or it was purposely left out because of issues that could or may be occurring with the machine. They want to have quick, easy access to remove that panel, whether they put one or two screws back in or all the screws are left out, which we found in cases, so somebody can quickly lift that panel up, which then leads into a potential hazardous situation. If a guard is designed to be bolted in, it needs to be permanently fixed with proper hardware. As you can see on the bottom right, there was hinges on a door that you can see is routinely removed, and even the replacement hardware is not the hardware designed for that hinge, where you're looking for a flathead style of screw or bolt to go into that door frame and that hinge hole. The top right, you see Phillips head screws, and we'll talk more about the types of heads a little bit later in the webinar. But what we find is things like Phillips head or slotted head screws are considered common hardware, common tools. And one of the things I first said is looking at common tools versus special tools. Common tools means that anybody can pull something out of their pocket on a reasonable fashion, and we'll talk about what that definition is, and be able to remove a guard. The interesting discussions you get into is if somebody took a tool to remove a guard, would that be considered willful intent? Everything we're saying could fall into a gray area, but most of the time what we've found that is not considered willful intent because you did not make it difficult for somebody to be able to do that. Whether they're motivated by production or trying to get things out for their job, they're doing things that they shouldn't be doing. When you have tamper-resistant hardware in there that uses that special tool that only authorized people have access to, they're no longer tempted to even defeat the guard because they don't have the capability of doing so. In the next slide here, special tools or keys left at the machine. What you can see in those pictures, whether they're electrical cabinets or guards that require a special key, in each one of these pictures, what do you see? The key was left in there for anybody to be able to access, which means it no longer requires a tool. It's just like having the thumb screw in that first set of slides that we presented. Being able to take that key and unlock that door or open to the guard. The one on the right is a key for either electrical enclosure or fixed guards that have like a square inset that uses that type of key handle. Well, having the key hanging right on the door frame or right on the frame of the machine gives anybody the access to do what we don't want them to do, to get into a potential hazardous situation with the machine. Having spare actuators. When you have safety devices that use a common actuator, and this happens across many different manufacturers, what you tend to find is whether it be operators or maintenance walking around with a keychain with the spare actuators for the sole and purpose of what is claimed as being troubleshooting a machine, but exposes them to risk by inserting that key in the door and allowing the machine to run in the full production mode and not having the protection. A maintenance person's life is just as important as an operator's life, but this seems to be more of a common practice than you would like to think. The picture on the right, you can see there's one type of interlock key. The picture on the left, you can see a key inserted into a switch being purposely bypassed. But if you look at the wire tie, there's 3 or 4 different other keys on there for different manufacturers of interlock switches, so they can walk around and do that across all the machines on their floor. The next one we see a lot more often than you'd probably think or want to know about is designed-in key switches with the sole purpose of either bypassing or overriding door safety devices. And you can see the labels: door bypass, either off or on; safety interlock override, enable, off or on. In both these pictures, what you see is not only is the key in there, the guards are being completely bypassed. This is a designed-in electrical switch with the sole purpose of bypassing guards. What you really need to do is look at the reasons of why that's even needed. Is there certain functions? Is there other measures that are taking place to reduce risk on the machine? How many machines do you run into when you, in the grand scheme of things, do you find really requires a guard door override to perform a certain job function. I think you're going to find that it's going to be very little, and there will be additional measures you can put into place to reduce your overall risk of people getting seriously hurt in a machine. The next one takes it one step further, electrical bypassing. When somebody has access to a control enclosure, what you see is the picture on the right is a series of contactors or motor starters. And if you take a close look, I know the picture isn't extremely clear, but all those contactors are being purposely pushed in and held in with screws being stuck into the top of the housings with the sole purpose of having all those motors turn on and stay on and not get shut off for safety considerations. The two pictures on the left and center are the same safety monitoring relay, but one's on the top side, one's on the bottom side. And it might be a little hard to see with the glare of the picture, but what's in there is a jumper wire. And in both those pictures, with that jumper wire, and you can see it's marked with electrical tape, for that sole purpose. It's not numbered, it's not part of the original design, but what those terminals are S11, S12, and S21 and S22, which are the redundant safety inputs. So what's happening there is the entire safety circuit has been electrically jumpered out in bypass and rendered mute as a safety function. Whether they were having issues with the safety system that they didn't know how to troubleshoot, this was purposely done, and all the safeties were now defeated on the machine. Definitely not a good situation. In this next slide, when we talk about willful defeat, here is some pictures of the one on the left is an electrical enclosure. That clamp was intentionally or could have been accidentally left open for anybody to open up an electrical panel. Whether there was just 24 volts in there, but more often than not, what you see is 120 single phase, 240, 480 three-phase. There's high voltage, or I should say not high voltage, hazardous voltage that anybody can touch terminals that they're not supposed to have access to. That clamp should be properly tied down with proper hardware, whether there's a padlock on the electrical enclosure. The center picture is a locking safety switch that not only was the key removed, the key and the switch were both removed and tied up into a corner of a machine that was willfully defeated so the operator could open up the door at any time, at any point in the cycle without interrupting the process. The two pictures on the right of the same scenario, it's a key interlock switch where you can see the one all the way on the right is the key inserted into the switch. Well, the picture just to the left of it, you see the socket head cap screws in that metal fixture or the metal plate of the machine. That's where the key was supposed to be mounted. Somebody took those bolts out, stuck the actuator key from the door in there, and put the bolts back and just tighten them down so they can open up the door whenever they want it without shutting the machine down. All of these situations lead to very dangerous conditions. Serious harm can occur, amputations, fatalities. It's one of those things that'll never happen to me kind of scenario. We don't want to get to that point. So we want to look at what can we do to try to prevent or minimize these type of things from occurring. So when we look at a standard like ISO14119, which is the standard for safety interlock switches on movable guards, it gives two definitions, a definition of defeat and defeat in a reasonable, foreseeable manner. And I use these as examples because you're starting to see a lot of the safety standards refer to these two terminologies. And part of it, when we look at defeat, it's to make something with the safety side inoperable, whether it's removing a guard, bypassing it, or defeating the safety interlocks that are on the machine. It can lead to serious harm. But what is defeat in a reasonable, foreseeable manner? Because that can become subjective really quick. what the standard tries to identify is grill down that gray area to have less subjectiveness to it. And when you look at it, it's the feed of an interlock device, either manually or readily available objects. So what does that mean? And you can see in Note 1 and Note 2, having tools that are readily available that operators need to perform their job function. Part of their job function may require them to make adjustments on the machine, do line changeovers, where they need screwdrivers or slotted head or Phillips head screwdrivers, or even to the point of Allen keys, hex keys, because they have to do changes of the mold in the fixture. Well, they become common tools, and if those bits of hardware are used on the guards or interlock devices, it's giving them that free, clear access to do things that they shouldn't be doing because they have the tools to do them. The second point in note number 2 is things that you can use in substitution, like screws where you saw in the contactors, being able to get to the control cabinet and purposely turning those contactors and locking them on with screws. Being able to use other objects to bypass something, such as keys that I'll show you. So this is the definition out of ISO 14119 of what a reasonable, foreseeable manner really means. So what we're going to look at now is how do we improve that guarding design? How do we get more tamper resistance in there? And here's just a few different ideas that kind of have a huge impact on your guarding design. Requiring special tools on the hardware that's being used on the machine. Unique actuators, and we'll explain what that means. Guard design changes or some of the additional measures. So we're going to cover those 4 different topics in the next set of slides here. So the first one, hardware requiring special tools. Special tools versus common tools we touched a little bit about, but slotted head or Phillips head screw bits are very common. Anybody can pull a pocket knife out of their pocket, which is reasonable to expect that somebody has the capability of doing it, or taking a dime out of their pocket, coin. People walk around with change in their pockets. Being able to loosen up a screw and remove it from a guard. You see a picture of a set of keys. Going through plants and audits, when we talk to people about having the proper hardware or getting into electrical cabinets that didn't have the lock change or a padlock put on them, or the hardware that keep the door closed, where there's still a slotted head screw, pull out a set of keys and see, I unlocked it and I can get into the electrical cabinet. It doesn't take somebody that's authorized to get in there. So these are common tools. You see a picture of a set of hex keys in there. Hex keys fall into the area where they could be special or they could be common. It's not reasonable to expect somebody to be walking around with a set of hex keys in their pocket, bringing it home from, or bringing the tools from home into the work environment with the sole purpose of bypassing guards. If you get that far with it, then it goes beyond just guarding. It goes to disciplinary actions. Why is that person still working at that facility that does that in order to get the intent of willful defeat or bypassing? But in cases like this picture was taken where these hex keys were right on a machine, because that was part of the tools that were given to the operator to do their job, which means the operator is capable of removing any guard on the machine because the machine did have either button head or socket head cap screws that require the hex keys or the Allen keys to be able to access. And in some cases, we find that operators are removing those as a result. So looking at some of the different types of hardware, you can see some pictures up there. It really has to come down to a decision. This is just more or less a guide for everybody to use, where what you see on the 3 left bits on the bottom of the page that's labeled Tamper Star, Tamper Hex, and Tri-Wing, you can't get at those pieces of hardware with standard or common tools. They need that special tool or that special bit that you can control and only have maintenance access to, where you put those in the guards to prevent that. Not only do you put them in the guards, on the interlock switches and the actuators, you put them in there to keep people from being able to remove them with the sole purpose of bypassing. The ones that you see no being the torque as well as the Phillips and the flat, I'm sorry, not the torque, the posi. The posi and the Phillips and the flat are common tools, because even with a Phillips, being able to take a slotted head screwdriver and getting into and biting on two sides of the X pattern in that bit, people have the ability of removing that hardware. The ones that are question marked in yellow there could or could not be considered special tools or common tools, depending on if the operators have that tool to perform their job function for other things, such as what we just talked about with the hex key, which is the third from the right. The star, for example, the reason why that's a question mark is, can you fit a slotted head screwdriver in there? Do they have standard Torx bits? Is it capable of doing that? If it's not, then it could be a piece of hardware that requires a special tool that tool is controlled. So there's going to be variations and interpretations of that, but when in doubt, you can always look at the first two on the left that are probably the most common tamper-resistant hardware, being the pin and hex or the pin and Torx type of screw bits that have the hollowed-out center in the bit because of the pin that sticks out through that piece of hardware. So the next thing we're going to look at is hardware requiring special tools. Taking it a little bit further, what you're seeing some of the standards call out, such as in ISO14119, is the ability on the actuators, for example, to not only put tamper-resistant hardware, but one-way screws, making it more tamper-proof, where they have to be drilled out to remove that actuator, and it's a maintenance process. The reason being is they don't want people to have the capability, even with the tools, to be able to remove that easily with the sole intent of bypassing. The next one we're going to look at in that list that we were talking about, what do you do tamper resistance, unique actuators. You saw the pictures of the keychain or the wire tie with the different actuators for the switches, because you can get switches like the mechanical key switch you see on the left there with a standard key that fits all switches. It's a standard part number. But you can also get some of these devices that are uniquely coded. So if you look closely at that picture of the actuator key, it doesn't look like the typical key. You got some high and low areas or little humps in the key. Instead of being a standard cam, there's multiple cams like tumblers in the lock to get into your house that have to be keyed. The key is now matched to that you can't walk around with a universal or a skeleton key. That key and that switch are a matched set. You damage the key, you replace the set. But we're also seeing to get it more tamper-resistant but be more functional with non-contact type of devices, we're seeing a trend toward the electronic devices such as RFID, which is the picture on the right, where you can get RFID type of switches, safety switches, that are also teachable. You can have them common with the same actuator, but you can also get them where they're individually teachable, where you teach the RFID tag to the switch, and as a result, you have a matched set. If you need to reteach the actuator, some are either permanent, and some you can reteach the actuator as a result. The next thing with guarding tamper resistance is guarding design changes. When you look at the overall design of a machine, now obviously this is much easier to do on brand new machines being fabricated versus retrofits, but even retrofits can take in some of these concepts. Mention having solid sheet metal panels that could cover up what's going on inside the machine. Does it really need to be sheet metal? Can it be Lexan like you see in the picture on the left? Even the tunnels are a translucent, like a blue translucent type of Lexan or plexi or some sort of polycarbonate material that you can see through it. You can see everything that's going on in the machine. It gives a clean look, but gives full visibility. So why do you need to bypass a guard to be able to see what's going on? Given full view. Even in the larger machines, having the full windows to see what's going on when the doors are in a closed position. Making sure all the controls, you're not reaching through the machine, which you see on older machines, having to reach through the process to actuate push buttons or selector switches or touch screens. Bring the controls outside the machine so you can perform all your normal operator duties and make sure they're pulled out. But being able to have that full guarding and changing the guarding design so you have visibility has a big impact on making it more tamper resistant. Also, make sure even with that you're using the proper hardware that requires special tools. Some additional examples that can be done, taking safety switches, instead of being full view, having them in a concealed location, meaning they're buried inside the machine, whether it's down in the track somewhere where you can't simply get to them because the guarding that covers those up, you can't get to that guard because of the proper hardware to get to the switch. There's a lot of effort to purposely go in there and bypass a guard, or mounting the safety switches out of reach. Fix worn or damaged machine parts. That sounds funny when we talk tamper resistance for guarding, but what you do find potentially a lot of times, especially on older machines, why are they getting in there so often to clear jams on the machine? A lot of times it might be because the machine has aged through enough where the mechanical parts have now become worn. And because of the worn parts, they're causing a lot of jams, which ultimately you start finding that whether it's maintenance or operators start bypassing guards to make it easier because they have to produce parts. If you're not producing, you're not making money. But ultimately, because of those jams that's constantly shutting down the machine, the guarding is taking longer to get the machine up and running, and you see production throughput get drastically reduced. Well, if you fix the worn parts that's actually causing the jam and have the proper guarding, you can even see throughput or production output be increased because of fixing the inherent problems with the machine to begin with, which caused or led to the bypassing of the guards themselves. Doing the random checks. Once you put stuff into place, do spot checks. Make sure you're checking that you're not seeing any issues with guarding being removed. We've walked into customers where we talked about what's happening on a machine, see a safety switch that was removed and off to the side, bring it up to them, and find out that when you talk to them, it's a frustrating point for them that, yeah, maintenance puts it back, and then the setup person ends up removing it again. They even went as far as putting some sort of epoxy or silicone to cover up the screw holes, and they would dig it out so they could remove the switch. There's something wrong with that, whether it's personnel issues or there's a design in the machine or the combination of the two, they need to be addressed. So doing random checks and routine audits to make sure the safety devices are fully in place and functional during different times of the operation of the machine. So that was tamper resistance. Now we're going to talk about fault masking, which I think a lot of people were aware of, but it never really drove more on what do we do about it because it went kind of unnoticed. So we're going to talk a little bit about fault masking, and this deals more when we're dealing with electromechanical safety devices. So dry contact, key interlock switches, or coded magnetic switches. Once you wire them in series to a safety controller, you have redundancy and monitoring. What does that really do, and what does that mean for us, and what faults can occur? Because what can happen is faults can occur in a safety system, and they can be masked or reset by opening or closing another door. And I'll show you a little bit about what that looks like. But before I do, a couple definitions right out of, there's a new technical report that the ISO committees came up with, TR 24119. They define fault masking as the unattended resetting of faults, preventing detection of faults by the safety-related part of the control system. That's what the SRP/CS means, safety-related part of the control system. Series-connected devices with potential free contacts. That just means dry contacts or hard contacts versus having solid-state outputs. What can be done with that? So they're the two things that we're concerned about when it comes to fault masking. So in the next couple slides here, I'm not showing you a complete safety circuit. I'm just showing you a representation of 4 doors wired in series, dry contact switches wired in series to a safety controller. What does that really mean? Ultimately, each switch has 2 contacts in there for redundancy. In case one fails, the other one makes sure the safety circuit shuts down. And because of that failure, the safety controller says, hey, I didn't lose that channel. There's something wrong. I'm not going to allow you to start the machine back up. So we're showing a representation here of just green arrows, just showing the flow into the safety controller. So when we go to the next slide, what we're going to do is we're going to open up door number 2. And you can see on the bottom, or the second rung, that contact opened up because of that safety, which shut down that green flow path into the controller. Machine shut down. But for some reason, we have a fault, whether it was a failure inside the dry contact of the switch itself, or there was a short circuit in wiring or cabling. That path continued to run. The safety controller did its job. It did what it was supposed to do. It's monitoring those circuits. It saw one path clear, not the other one, so it's not going to allow you to run the machine or reset the machine. The problem with this is, too many times what happens is you're not just opening up one door. You could be opening up 2, 3, or all 4 doors to refill something or clear a process or something jammed that you had to clear out. They go and open up door number 3. Well, what did door number 3 just do? It cleared the fault. The controller saw both channels clear out now. This is what's called fault masking, because that fault, even though it was originally detected, now went undetected. It was an unintentional reset of the controller just by opening up that other mechanical switch in the system. As such, when we close all the doors again, even though that fault still lies in door number 2, because both channels were clear, we got both paths, that safety controller is able to reset the machine now. The same holds true if you open up door number 1 or door number 4. But if you open up door number 1 first and then door number 2, the fault went completely undetected, even though it's sitting in the system right now. So what can happen is an accumulation of faults. So we had a fault in the first channel. We could potentially get a fault in the second channel. So when we open up door number 2, what happens? Absolutely nothing. The machine keeps on running at full speed because of fault masking. We knew about this, but now that we have a technical report on there, there's things that they address on what can be done and what are the considerations of what we look at. So they can combine the concepts of ISO 14119, which are interlock guards, and then the performance levels with ISO 13849, and specifically talking about the diagnostic coverage. What does it take in consideration is the number of doors, how far apart they are, how frequently they're used, because the more frequently doors are used, the higher the chances of fault masking to occur that could, over time, lead to an injury. So what do we do in cases like this when we have to accommodate for fault masking based off of how the machine is designed, how it works, how the safety system is put into place? So what we're looking at is looking at wiring techniques, prevention and design from the faults from occurring to begin with. So why would we get short circuits and open circuits? A lot of times we're using multi-conductor cable in the machine. Well, if that cable gets crushed or sliced through, it can easily short out. But when the cable is put into what they're calling protective wiring, meaning whether it's EMT or more to the point rigid conduit, what's the likelihood of crushing those wires and those cables inside the machine that actually causes those faults. Separating the signal paths so you don't get that fault because the paths are separated. You don't get that chance of a quick short within a wire or cable. Don't connect them in series. Run them all directly back to your junction box or the main control box, and also put them on their own safety set of inputs to your safety controller or a programmable multiple I/O safety device. But more often than not, what we're seeing the generation lead to is more electronic-based safety switches, because the electronic-based safety switches do their own short recognition, cross shorts, as well as shorts to voltage and ground, that a fault masking cannot occur because the switch did not clear its fault. Because of the electronic-based microprocessors inside, it won't allow fault masking to occur. So they were the couple different avenues of taking with fault masking. I know I went through that fairly quick, but without going into a lot of details on doing full schematics and going through different scenarios, we wanted to give you a general overview of what fault masking really is. So at this point, what I'd like to do is, Travis, if we can open up the questions.
All right. Well, thank you very much, Mike. That was really phenomenal all the way through, and perfectly well timed after that. Now we already have a ton of questions in here. We're going to get to a lot, but please keep them coming in, and we'll jump on them as soon as they come. All right. So I guess the first question for you, Mike. Can guards be attached with thumb screws to allow for ease of preventative maintenance?
They can be attached with thumb screws if you put interlocks, safety interlocks on them, because when you attach it with thumb screws, they're no longer a fixed guard. They're a movable guard, where just like having a door on a hinge to gain access. But the other aspect that you have to be careful of when making that decision, even if you put a safety interlock switch on there, the one thing that you had just said in that question was for maintenance reasons. You really have to look at, and if you haven't attended the webinar back in December, go back and view that recorded webinar on lockout, tagout versus machine guarding, because ease of access for maintenance, is it a normal, routine operator task that would fall under the machine guarding standard where you can use interlocks for? If it's a maintenance task, most of the time maintenance tasks could fall under a lockout-tagout condition. And if it needs to be locked out and tagged out, the safety switch will definitely be good to keep the machine from running, but to rely on that without implementing lockout-tagout is definitely asking for trouble. So you want to ensure that the task that you're performing either falls under lockout tagout, or if it does fall under machine guarding where you need to gain access while the machine is running to do an index or a jog, what safety circuits are in there, can you justify it? Make sure you do a task-based assessment to know that this can be a safety interlock condition. Otherwise, it is lockout tagout, and thumb screws still wouldn't be good unless an interlock switch is on there. And if anything you do falls under lockout tagout, why even have the interlock switch? You're better off making sure you have the proper hardware that people can access. And the reason I say that and made that a long answer is because in the question for maintenance tasks, for quick, easy access for maintenance, well, what prevents an operator from removing that panel to do something that they shouldn't be doing if it's not a normal routine task that is performed? So I think you get into a little gray area with that, but at absolute minimum, if you're going to put thumb screws in there, have some sort of safety interlock because it now becomes a movable guard. But you really need to take it back even further to determine, is it a lockout tagout condition, or is it a machine guarding issue that you have to contend with. But if it's a normal routine maintenance task, we have to question, why do we need that much access in that guard if that's not supposed to be routinely accessed, if it's designed to be a fixed guard? Is there an inherent problem with the design of the machine or parts that have worn that they need that routine access? So, and I'm generalizing, but you really got to look at it as a case-by-case basis.
Perfect. Good. Thank you. All right. So this next one, I think this is important for a lot of people out there. So who is legally responsible if the safety system is bypassed?
Ooh, I'm not a lawyer, so I'm going to answer this the best I can with not being a lawyer. Ultimately, what it's going to come down to is anybody that has to do anything with that machine. If the machine was designed from bypassing from the OEM is definitely going to get pulled in. Ultimately, it's the end user, the owner of the equipment, that is liable for that. So if somebody goes in there and bypasses, the owner is going to be responsible if somebody got hurt for that machine. The problem with that is what you're going to end up doing is go into a court of law, ultimately potentially go into a jury trial if it's not settled out of court, and it's going to come down to the person who got hurt against the company. Now, whether you can prove of willful intent at that point because of putting the tamper resistance in there, I can't make that decision because that decision is ultimately going to come in on how good the lawyers on both sides are and what the feelings and emotions are of the jury that's basically over the case. Now, part of it, what ultimately comes back when you hear a lot of these stories of somebody getting hurt, is what you find out is it may be a common practice that was unwritten but an accepted practice within the company. That's not going to be hard to prove in a court of law, which will put the liability back on the company. But if you put proper tamper resistance in there and you still see people willfully defeating, you have to take actions as a company or an owner of a company that does something, whether it's reprimand, whatever your policies are, whether it's 1 strike you're out, 3 strikes you're out, whatever the case may be, written notification. This is not acceptable. And I've seen a lot of companies start going the other way, that if they violate a willful defeat of machine guarding, they're gone, because they'd rather have them not working for them and keep all their digits at the end of the day or their life versus exposing themselves or somebody else to that company, which risks injury. And ultimately, it could be the best person or the best operative you ever had on that machine, and it's been there 20 years. And I hate to say it because people do work good, and most of the time they work with the good intentions. But doing willful defeat, even though good intentions may be behind the scene, risks serious injury. You do not want to get into that situation. If somebody's willfully defeating something, it's not just an automatic, why are you doing that when we make it tamper resistant? You want to investigate. What is the reasons? Is there a root cause somewhere? Is there something wrong with the machine that has to be fixed? Which is why you want to run your routine audits or your spot checks to ensure safety is being done. If you find things such as the willful defeat, and the more you walk around in a facility, you may see more things than you ever thought or wanted to see because of now inspecting these certain areas. Why is that being done? Or if you see covers off, why is that cover off? Get to the root cause of what the reason is, fix it so you don't risk somebody's injuries. But ultimately, it could be the company that's liable. It could be an OEM. It could be a faulty in a component that a component manufacturer gets pulled into. It could be at the liability of the person that did it because they knew the ramifications. They had a policy in place, and nobody knew that they violated that policy. But ultimately, it comes down to a court of law and who decides who's responsible.
Good. Thank you. Now, jumping straight into another one. I was kind of wondering this myself. Can you give examples of why a machine manufacturer would install a bypass or an override?
In some cases, the terminology may not be proper. Even though they say door override, it's really not an override. It might be a setup switch. So, for example, on when you look at certain Type C standards, which Type C standards are the more integral design standards on functions as well as safety on a machine. A CNC machine could have a setup mode that requires a key switch that allows them to open up the locked doors in order to jog a X and Y axis for setup purposes using something such as an enabling switch or two-hand control as built by that design standard. But the spindle is not allowed to run because of the hazards associated with the spindle, but they can do setup, which they may have to be up close and personal and do some indexing and jogging to get the piece set up right, then close the door, come out of that mode. So sometimes it's mislabeled. I've seen cases where it was requested by the customer. The customer requested that switch to put in there, so the OEM did what was requested of them. Now, whether they got indemnification or they just put it in because of the request that allows them to bypass those guard doors, sometimes they're there because it might be not an operator bypass, but it's designed to be a maintenance override. But unfortunately, they just jump around the safety devices without taking into consideration of forcing it into a jog or an inching mode and monitoring the speed of that function to reduce the risk for maintenance setup, for example, or a changeover to that point. Other times it could be that the customer installed it themselves because they felt it was necessary and wanted to be able to override it for ease of access. So somebody decided that that was a standard and they were allowed to do it, not really understanding the implications and ramifications of that choice.
Good, thank you. All right, so next one, what are the OSHA expectations for non-common hardware?
When you look at some of the additional OSHA information, a lot of the stuff that I've seen just calls out for not having, I'm going to say, requiring a tool to remove. But when you look deeper into some of the OSHA standards, there's not always a lot of reference. Some of it's a special tool, some of them don't. It's varied on what the interpretations are when you look at interpretation letters. But ultimately, what OSHA comes back to is recommending and encouraging people to use industry consensus standards such as ANSI and ISO, as they're going to be more detailed and more up-to-date on some of the things like the 1910.212 standard. However, they make a stipulation that industry consensus standards do not override an OSHA standard, but they're used in complementary to OSHA standards. So referring back to that, that's usually what it comes down to, and we're seeing more and more of the inspectors going hard at some of these different aspects, because I know that under OSHA this year there's a national emphasis looking at machines that have amputation hazards. They're seeing that influx of amputations, which is drawing OSHA's attention, and it's gathering a lot around the machine guards. So there's nothing specific that details you must use this type of hardware. It has to be a tool to remove, but ultimately it comes down to a court of law to determine was that tamper resistant, was it a common tool? Did you give them the tool to perform that job function? Should they be removing guards? No, but they're performing line changeovers, so you gave them a set of hex keys, so socket head cap screws to remove a guard to clear something out when they shouldn't be doing it, but you gave them free clear access to do that. So it gets a little gray.
Well, good. Actually, I have another gray area question here. So one of the listeners wants to know: is it fault masking when there's a fault and someone just turns the machine off to reset the fault?
Potentially, it could be, because when you have a series connection dry contact type of circuit, what can happen is if you shut power down to that safety circuit and turn it back on, the controller has been reset. So it can classify as fault masking upon power reboot. So that becomes, and like you said, it becomes a gray area. It depends on the use, and under normal operating principles, who's allowed to throw disconnects on a machine and cycle power to that. Ultimately, it does come down to a training issue, that when you have that potential situation, if you open and close a door and the machine doesn't restart, that's your flag to call maintenance, because there's something wrong with the safety circuit. The safety circuit actually did its job. It stopped the machine, allowed you to do what you needed to do, but prevented you from restarting because of the fault that's in the system. So if you cycle power and say, oh, it was just a ghost problem, it's not a ghost problem. It did its job. So part of that is, one, if that's a potential issue, yes, you have to consider that. And in considering that, how do you do that? Well, part of it is you do individual controllers where you have to cycle test the doors before the controller will reset. So you got to open the door and close it, and if that fault's still there, it won't allow that controller or that programmable controller to start. If you use electronic safety switches, just by cycling power and you turn it back on again, if you haven't cleared the fault's still there. So under electronic switches, fault masking can occur even with a power cycle, because as soon as you power up and the microprocessors evaluate its channels, its inputs, its outputs, and if it sees a short circuit, whether it's to each other or 24 volts or a jumper to 24 volts, it's going to prevent its other output from turning on as a result.
Good, thanks. I think we still have time for a couple more questions. We still have plenty coming in. So here's a question that came in from a machine integrator. How would you address troubleshooting when the machine is still in final assembly and needing to be tweaked?
As far as a machine integrator or the machine builder is concerned, I know that comes into a problem in regards to the machines being built, and you could be designing something completely custom that's never been made before. But what you have to do is, the best way I can word it, and I tell people this, is you play the what-if game. What if this were to happen? What is the outcome? And ultimately, is there a reason that you need to tweak why the machine's running? Is there a mode that you can install in the machine? Is there a reason not having the guarding in there? I know it's more inconvenient in opening and closing guard doors all the time, but what is the alternative? Being able to quickly adjust something while the machine's running, but also risking your finger or your hand at the same time. Being able to remove the pressure. If that's not possible, and again, I'm generalizing because every machine is different, but if that's not possible, and during a machine build that you have to run certain things without the guard in place, what other measures can be put into place to protect your own workers? We know that ultimately when you ship the machine to your end user or your customer, it's going to be fully guarded so they can't get into the same access without the guards because of that. But when it's in your floor, it doesn't make your people less valuable to do their job as well. So what other measures can you put into place if the guard really has to be removed? So that's the what-if game. Do I really need to do this, or is it convenient to do it that way? Okay, I have to remove the guard. Well, can you install, instead of the guarding that's supposed to be on there, a two-hand control that allows them to turn that safety controller on and allow them to index the machine with two-hand control? That way their hands are out of it to perform that function and quickly be able to do what they need to do, but the machine is not capable of being run unless you actuate the two-hand control. Maybe you need to have a hand-free. For example, printing presses, sometimes adjusting the guides on them or the print heads can't be done at a standstill and may need to be done in a running motion. Well, can you have inside guarding that tools reach through the slots? Can you open up the door but have a three-position enabling switch to perform that mode? So there's things on an OEM side that if you figure that in on the front end when you're designing that machine, that you're going to put this temporary safety circuit in, even if it's one you build for your machines that you just install as you're building the machine and then pull out for the next machine that you're running. There's things that you can do that reduce the overall risk to keep somebody from getting hurt. Why do I say that? is because I have run into situations and seen it live. I've seen machine builders do troubleshooting, and because they have to make adjustments because things catch, they're not perfectly aligned, and all of a sudden something jams. Well, because of not having the guarding on the machine, the first reaction of human nature is to reach into the machine and clear the jam. And what had happened in certain cases, one case I saw they cleared the jam of a pallet out of an elevator, and because there was residual pressure, the thing took off on him and sliced through his finger and cut through his tendon. Where if he had an enabling switch or an e-stop that was readily available that dissipated the air pressure to avoid that motion, it wouldn't have taken place. I've seen another case where somebody was trying to troubleshoot something, and what did they do? The guard wasn't installed. They reached in, and they hit a limit switch, which activated an escapement cylinder because nothing was shut down, and the escapement cylinder punctured through his finger. But the escapement cylinder with that puncture did not create the most serious injury. It was a puncture at that point in time. But human nature, when you feel a bite, is to retract back and pull. He pulled and ripped through the tendons of his finger and needed surgery as a result. Both cases of an OEM. It's nothing that we ever want to see from an end user or an OEM. So I would seriously look at what can be done to protect your own people while building the machine to be able to safely operate it, and really just raise the question, can it be done with the guarding in place? Okay, it's a little more inconvenience, but convenience is not a sacrifice for safety. If there's a specific reason, what other measures can be put into place to protect your own workers to make those adjustments?
Fantastic. Thank you very much. And we'll have to call time there. We're a little bit over. Thanks, everyone, for sticking with us. On behalf of New Equipment Digest, I'd just like to thank our speaker, Mike DeRocher, for that really fantastic presentation this afternoon. I'd also like to thank Schmersal for making this webinar possible. And, of course, I'd like to thank you, our audience out there, for all of your time and attention today. We hope you found this webinar valuable and that you'll return next time for our future webcasts. So, everybody out there, have a great day, and see you later.
Thank you, everybody. Have a great day.